Good day, I'm Dr. T and welcome to my office. So, as chemists, we deal with chemical reactions. And of course, we need a good way of describing and talking about them. So today I'd like to talk about chemical equations. And to do this, I'm going to bring in a very common reaction that as chemists we like to talk about because it's very, very important and it's got some really interesting history on it. If you'd like to read more about the history of this one, I recommend a book by the title of Alchemy of the Air. It's a nice, fun read. But anyways, the reaction. This is going to be the Haber-Bosch process. And in this case, what we have is a reaction that makes ammonia. Ammonia is an absolutely critical industrial and agricultural chemical. This is used heavily for industrial fertilization. So if you've got, a farm, not a garden, but a full-on farm, this is a very common way to fertilize. And even if you've got a garden, the ammonia, or I should say the nitrogen in your fertilizer, almost certainly started out as ammonia from this particular process. Approximately 1% of the global energy supply, which, that's a lot, goes into this one chemical reaction, which is, insane. Okay, so in this chemical reaction, what we're doing is we're taking hydrogen, which we typically acquire from petroleum products. You can acquire it from water. That's more expensive, though, with current technology. Then you're going to react that hydrogen with nitrogen that's just pulled from the atmosphere. And you're going to react those two at ludicrously high heats, at ludicrously high pressure, with I believe it's an iron oxide catalyst. And you're going to use that to make ammonia. And then ammonia is an incredibly valuable product. Not gram per gram, but on a large scale. Okay, so the hydrogen and the nitrogen are what we call reactants. These are your starting chemicals. You react them together and you get stuff, specifically ammonia. Okay, the ammonia is the product. So the reactants, the hydrogen and the nitrogen, react to form the product, which in this case is ammonia. We will usually write this out by writing the chemical formula of one of the reactants, and it depends. Some reactions, there's only one reactant there. That doesn't have to be two. There can be more than two. There can be less than, one is the only other choice for less than two. You have to have at least one. Okay, so you're going to have your reactant or reactants, and they'll be separated by plus signs. If you read them out, you'd say the chemical name and you'd say "and" when you read a plus sign. And then you will come to the arrow, and you will pronounce the arrow yields. So in this case, I would say hydrogen and nitrogen yield ammonia. Okay, now the arrow actually comes in two flavors. The typical arrow that you see the most is just a normal arrow, and, it's an arrow. This indicates that reactants form product and that it does not go back. There's something about that chemical reaction where there is no meaningful conversion of products back into reactants. The other arrow, which is what's present on this one, is an equilibrium arrow. In that case, reactants form products, but there's a meaningful conversion of products back into reactants. And what will happen if you let this reaction go long enough is that you will have a blend in your reaction container of both reactants and products. Individual atoms will go from reactants to products and back, but eventually the blend will stabilize, reaching what we call a dynamic equilibrium. More on that later, but I do want to give you a heads up that there are two different types of arrows, and the assumption that the reactants turn to products and that's it is only valid for certain reactions. Okay, now let's look at some other information we can provide here. Sometimes we'll stick information above or below the arrow that could indicate things like adding heat, solvents, or catalysts. Things that are important to the reaction, they're involved with the reaction, but they're not actually in the actual reaction. They're things that are affiliated with, not part of. Okay, also looking at these guys, we have what we call coefficients. So you'll notice in front of the hydrogen and the ammonia, there is a 3 and a 2 respectively. This is telling me the ratio of atoms / molecules that are reacting. So this is telling me for every 3 hydrogens, they're going to react with 1 nitrogen. There's an invisible 1 in front of that nitrogen. We don't write ones. We don't write ones in the subscript, and we don't write ones in coefficients, but they're still, effectively there. Okay, so this is saying 3 hydrogens react with 3 nitrogens to yield 2 ammonias. Yeah, this is giving me the ratio. And this ratio, when it's present, is referred to as a balanced chemical equation. And any chemical equation to be useful really pretty much needs to be balanced. We're going to jump into later on a topic called stoichiometry, where we're actually using these ratios of atoms to figure out how much product will be produced from a certain amount of reactant, or how much reactant is needed for a certain amount of product, or how much of each reactant you need. Any kind of combination you like with looking at quantities. The way you balance them is you're looking at the individual atoms. There's this idea of conservation of mass. In reality, it's just the atoms stay there. They don't go away. You can't magically create an atom, and you cannot make an atom disappear. So if you look at this, I've got 3 hydrogens. So that means, because hydrogen gas, unfortunately the elements share the name with their atom, so H2, or hydrogen gas, has 2 hydrogens in it. If I have 3 H2s, that means I have 6 hydrogens total. So if I look on the reactant side, I have 6 hydrogens. If I look on the product side, I still have 6 hydrogens. Ammonia's NH3, it has 3 hydrogens, there's 2 of them, so 6 hydrogens. Same for the nitrogen. I've got 2 nitrogens to start with, because it's 1 nitrogen molecule, 2 nitrogen atoms, and then ammonia, 1 atom per ammonia, but I have 2 ammonias, they balance. And what I'm going to do is, just when I'm balancing them, what I'm going to do is go back and forth and just making sure the atoms are the same on both sides. It takes a bit of practice, a little bit getting used to. Basically, you just pick 1 atom and go back and forth. Typically, you can get a feel for which ones are going to be the easiest to start with. And so start with something easy. Now, I should make a quick point. You can change the coefficients. Don't change the subscripts. The subscripts, if you change those are different chemicals. It's a completely different reaction. So you can't change the subscripts. Only change the coefficients when balancing. Okay, so a little bit more information on the reaction. If I'm looking at this guy, I can see a little bit more information. You'll notice after some of these guys, so in this case, they're all going to have parentheses, G parentheses. That's telling you that they're in the gas phase. So these are state symbols. Now, depending on my reaction, that could be a parentheses, L parentheses, that's liquid. So if I had, say, water involved, obviously this thing is running at like 600 degrees Celsius. So everything's a gas, at least every little molecule you might be working with. But if I was to, say, work with, say, room temperature water, obviously that would have an L at the end of it. So parentheses, L parentheses. If it's a solid, then parentheses, S parentheses. And if it's something dissolved in water, water is such a common solvent, so many reactions take place in water, it actually gets its own state symbol. That's parentheses, AQ, close parentheses. And that's AQ for aqueous. And so it's fairly straightforward. 2 parentheses, and then the first letter or 2 letters of whatever state it's going to happen to be in the middle. They're lowercase letters, but they are full size. Some folks, myself included, I have a bad habit, will write this as a subscript. They're not a subscript. That's usually written as a subscript because you didn't leave room and are trying to cram it in on the paper. They are meant to be full-sized state symbols, full-size letters, just normal lowercase letters. So with that said, have a wonderful day.